Hello everyone. We will now continue on our journey into embedded C programming, and what we are going to look at in this set of videos is some of the basics of embedded C. To some extent, how it differs from regular C, what are the things that we primarily care about. To some extent, this is also a very quick recap of what is there in regular C, but for the most part the assumption is that you already are familiar with C programming as such. So we are going to start off with the concept of writing efficient C code for embedded systems, right? And in particular, there are a few things that we need to understand over here. We'll be starting with a recap of what C programming actually is, then look at the topic of efficiency in a little bit more detail and what it means to actually design systems that are efficient in the context of embedded systems. Okay, so first things first, we have already sort of discussed this briefly, but C as a programming language, why does it even exist and why is it a useful language to know, right? Now why does it exist? Of course it's been around for a very long time, about 50 years or so at this point, and when it was introduced it was primarily brought in as a language that allowed people to write operating systems. In other words, the development of C went hand in hand with the development of the Unix operating system. And that shows in a number of the sort of basic primitives that are available in the language and the kind of problems it is best at solving. Now why? And if we keep this background in mind, it becomes a bit easier to understand what is special about C. In particular, it is close to the hardware. What that means is that if you look at a piece of C code, it is usually possible for a reasonably experienced programmer to be pretty much able to say, okay, that this particular C code is going to translate into these assembly language instructions. And for the most part, you will probably be right. You will have at least a good overlap with what actually gets generated by the compiler. It is possible to create more complicated data structures and so on, but that's not what we are talking about. We are talking about the basic parts of the language itself. What that in turn means is that since you are so close to the hardware, it gives you very fine-grained control over the system resources. What are system resources? The most basic resource available to any computing system is of course computing power, the number of clock cycles available for doing useful work. But apart from that, it is the amount of memory that's available in the system, the storage, the I/O, the input output, network bandwidth, various other kinds of features like that, which also have to be sort of controlled and given to the programs that need to use it in different ways. Now, while allowing you this level of control, C also provides the capability for structured programming. There is a concept of functions, there are loops and other kind of iterative keywords and execution constructs, and there are ways of taking different types of data and putting them together to create more complex data structures or data types. So this allows a higher level of abstraction. So all this is to sort of explain why C as a programming language hits a nice balance between being close to the hardware, giving you direct access to what a computer is capable of doing, while at the same time providing a level of abstraction that makes it reasonably easy to construct fairly efficient programs. Now that word efficient is something that I keep using, but there are some very specific definitions of efficiency that we will need to sort of look into as we move further. Please keep that in mind. It is one of those terms which is broadly misused because people say things are efficient just when they mean that it's maybe well written code or it's not particularly wasteful, but it is usually possible to almost quantify that in many contexts, and that is something that we will try to do as we move forward. Now, as I mentioned, where does the C language get used? One of the main areas where C really shines is in the creation of operating systems. Like I told you, it was already originally written in the context of the Unix environment, and Linux, the Linux kernel, the actual kernel of the operating system, is also written in the C language, right? And there is a reason for that, which is precisely the fact that it gives you fine-grained control over resources, and at the same time it translates in a very straightforward manner from the C code that you write into assembly language code that runs on your processor. Now, another place where C actually shines is in high performance code. This includes scientific computation or memory intensive applications Similarly for databases, mostly things that are really pushing the hardware that you have to the limits of what it is capable of doing. And another area happens to be network applications. Once again, these need to strike a balance between the simplicity of the code that you write and the speed that you can get for actually transferring data. Another interesting place where C does get used quite a lot is in game development. Of course, there are reasons in game development to go for higher level abstractions like C++ or other kinds of object-oriented languages. But just the raw performance that you get by writing code in C makes it still a very popular language for developing games. So what we are going to do is just very quickly have a recap of some of the basic concepts in the C language. Please keep in mind that this is by no means a replacement for actually going through a regular course in programming in C. Well, not exactly a course. What you need more than actually attending a course is practice. You need to actually write code, right? So please keep that in mind. The entire course on embedded programming is going to assume that you already know sufficient C to be able to do something useful, but it's not going to teach you enough of the basics of C. And at the end of the day, the only way that you learn any programming language is through practice. You cannot just read a book and learn a language. You need to practice actually writing code in that language. It's similar to human languages. Just reading a book will only get you so far until you start actually speaking in the language to other people who actually use the language on a regular basis. Alright, so coming back to C. The first thing that we need to keep in mind is that there is a concept of data types, right? And these are used for storing and manipulating data. The most common data type in C, or very likely the first one that you are likely to encounter, is probably the int or the integer data type. Right? And depending on the type of processor that you have, that integer data type is very likely to be a 32-bit number. Right? And then of course there is the char or the character, which is usually an 8-bit data type. Right? And on top of that, there are a few more sort of slightly advanced data types like floating point numbers, double precision floating point numbers, and shorts, where a short is basically a smaller version of an integer which uses less space. Now, all of these are common in any C programming. Now, the sizes are usually implementation dependent. The standard for C only defines sort of minimum sizes that are used in order to implement each of these, but there is a range of different values or number of bits that you can use for the size of an int or various other data types. Now, implementation dependent may be okay in the context of something like a general purpose C program which you are trying to run on top of an operating system and make it portable. But in the context of embedded systems, that's not really very helpful, because over there you usually want very fine-grained control over how many bits are being used by the system. And there is a header file in C referred to as stdint or standard integer.h, which actually allows us to use many other data types. In particular, it defines things like int8 underscore t, uint8 underscore t, which is an unsigned 8-bit integer, int16 underscore t, which is a signed 16-bit integer, signed meaning that it uses the 2's complement representation to store numbers, and so on. So in embedded systems, as we will see as we progress through this course, you usually don't want to waste space, right? The amount of space that's available to you for storage and for computation is very tightly restricted, which means that for the most part you are interested in using exactly the right number of bits for any computation that you need to perform. So this is a sort of quick recap of the basic data types that are there in C. There are more complex data types that you can create, the most common being the struct, right? It's the keyword struct, which allows you to encapsulate multiple different data which could be of different types. You could have an integer, a character, possibly even a string, all of them as fields of a single data type. Now, fundamentally it is not absolutely necessary to use structs as with pretty much any other part of this language, right? Part of the reason why these kind of keywords and these kind of constructs in the language become useful is because they help you to make your code more readable, understandable and maintainable. And this is yet another thread that we will be sort of stressing upon multiple times as we go through this course, because just writing code alone in order to solve a problem is usually not sufficient. You want to write it in such a way that somebody else can understand what you have written. Well, that somebody else could be you 6 months from now. So please keep that in mind, that you 6 months from now you are not going to remember your thought processes when you wrote code today, which means that choosing the right kind of data types, choosing the right kind of structures can make a big difference to how easy your code is to read and maintain as you move. Now, there are also enumerated data types and unions, which are once again slightly more complicated structures that you can create in C, and they have their uses. In fact, enumerated data types in particular do find use quite a lot in embedded systems, because they can be used either to sort of construct state machine based systems, or also to enumerate the different kinds of inputs, outputs, bits and so on that you might have somewhere as part of an overall system that you are designing. Union data types are kind of interesting. They basically allow you to have two different views of the same set of bits in memory, and there are specific cases where they are useful, although for the most part structs and enums are probably going to be more common in terms of what we regularly use. Now, the data types, once you have data, you need to be able to do something with it, and there are a few important structures or programming constructs that we use regularly while writing code. First of all, we have conditional execution, denoted by the if and else keywords. What we have over there is this is a very common use case. It basically allows us to choose between multiple different options. If some condition is satisfied, do something, else do something else, right? And for example, in an embedded system, it could be something like, if the water level sensor is showing that the water level has reached a certain height, then we need to turn off the motor, else we keep the motor running, right? Or if it has reached a low point, we turn on the motor. So those are simple things, but of course, exactly the same thing holds in a regular C program as well, right? So you could also chain these if else conditions. So you could have if the first condition, else if another condition, else if another condition, and so on. Now that's perfectly fine and valid, and a reasonable way of writing more complicated kinds of structure, complicated kinds of code. One of the examples would be, let's say that you are in charge of assigning grades to students based on their marks. You might have a condition which looks like, if the mark is greater than 90, then give them a top grade in S. Else, if it is greater than 80, then they get an A. Else, if it is greater than 70, then they get a B, and so on, right? Now, these nested or chained if else statements in some cases can also be replaced with what's called a switch case statement, which basically says I'm going to switch my operation based on the different values that I might obtain. And by choosing different specific cases or conditions, we can have a very compact way of representing different kinds of code. So keep in mind that pretty much anything that can be done with switch case can also be done with if else, except that this is a more compact and cleaner way to express many different kinds of code. Now those are the conditionals. On top of that, we also have something called iteration or repetitive execution of the same code, right? And we have a few different options over here, the most common being of course the for loop, right? And a for loop, what it does is, it basically says that a certain piece of code, which you then specify as the body of the for loop, needs to be run a specific predetermined number of times. Usually predetermined, it is possible for loops to have a variable number of iterations or something which changes and can be only determined at runtime. But for loops are usually used for the case where we know exactly how many times it is expected to run. While loops are a bit more flexible, what they allow you to do is write a simple condition which says, as long as that condition is true, execute whatever is inside the body of the loop. And modifying that condition or changing the parameters of the condition can happen anywhere inside the loop. So you can always execute a for loop using a while loop, And in the context of C, it is also possible to write a while loop using a for loop, although that's not a common scenario. For loops structurally are meant to be for things which are just repeating the same thing a fixed number of times or some known number of times. Whereas while loops are very generic, they could even keep iterating based on whether an input has been received or not. So those are the most common forms of looping behavior that we have. And one thing which actually turns out to be relatively common in embedded systems especially is the concept of something called an infinite loop, where we basically just keep on spinning, checking on some particular value. It would usually be written as something like while 1 or so, which basically means while 1 is never going to become false and you are going to keep on repeating that loop. But the fact is that somewhere inside that loop we are going to check some condition, and if the condition is satisfied we will break out of the loop. So break and continue are things that allow us to change the flow of control of these kind of loops. So all of this allows us to do something called control flow, which is changing the next instruction or next statement that is going to be executed as part of the program. And that is one of the most important parts in terms of the power of programming languages. And it allows us to create what are called structured programs that we can easily understand and reason about. Now, so far so good. You can actually do quite a lot of programming just by knowing data types and the basic conditionals and for loops and loops. But one of the really powerful portions of the C programming language comes when we start looking at functions. And functions are basically a form of reusable code, right? You take a piece of code that you find that you are going to execute regularly multiple times, and possibly you assign certain parameters to it, which we call function arguments, things that can be used in order to change the behavior of the function. On top of that, a function can also have a return type, meaning that it can be used in order to compute something based on the parameters and then return a value. The most common examples would be something like maybe the square root of a number, or a factorial of a number, or a sine of or cosine of a number, right? All the mathematical functions that we think about can usually be implemented using equivalents in a language like C, which is why the name function of course comes, because it is very closely related to the concept of a mathematical function. It takes certain inputs and transforms them into outputs. Now, functions in C can do a lot more than that, in particular by enabling the ability to update a value somewhere in memory through a pointer. We are not really restricted to just having a single return value. Now, this enhances the flexibility of functions. It also makes them a little harder to reason about. So, you need to use this with a little bit of care. As we will see on multiple occasions, anything to do with pointers you need to handle with care, right? They are extremely powerful, but they are extremely powerful. You have to be careful what you do with them, okay? So, all of this, the main thing that the concept of a function is enabling for you is what's called modular design, right? It allows you to break your code into a set of modules, separate functions. It improves the readability and maintainability of your code. And by effective use of various language features like header files, includes, function prototyping and libraries and so on, it's possible to get very well structured code that can also be reused systematically as required. Now, functions also bring in the concept of variables that are used inside the function, and in particular the concept of scope of a variable. And here we need to understand specifically there is something called a stack and a heap, and these are basically areas of memory, right? And all this was discussed in the C programming course, and it's probably worthwhile to go back and recap it because it turns out to be quite important in the context of embedded systems. The stack in particular is a specific area of memory that is given to each function call, and it is one of the things that enables the use of recursion, right? The important thing is each function has its own stack area, which means that it creates its own local variables, things that only that function knows about, and nobody else anywhere in the program has anything to do with those particular values. But it also allows you to pass data back and forth between the caller function and the callee function. So the callee is the one that's being called, and the caller is the one that's doing the calling of a function, right? A function call basically means that we invoke a function or jump to the start of that function after having set all the parameters we want to evaluate it for. And after the function has been called and evaluated, it returns, right? It may either return a value or it may just return without a value but having set some other parameters in other places. So all of this is enabled by the stack, but there is also a chunk of other memory that is called the heap that is used for general purpose storage, right? Things that do not belong necessarily to any single function. They could be the global variables that are used by the entire program, or they might be what are called static variables used inside a given function but which need to be kept permanent even after the function exits, or they might correspond to what's called dynamic memory allocation, where we just ask for a certain amount of memory and it is given to us in order to use as we like. Now, careful management of this scope plays a vital role in implementation of embedded systems, in particular because embedded systems tend to have long running code, meaning that very often you have something which once it starts just keeps running, possibly for days or months or even years on end, right? And all that it's doing is waiting for some inputs and responding to it. So when you have something of that sort, you cannot really afford to just create variables or use memory as you like, because after some time you will run out of memory and the system is probably going to crash. So you have to be careful with how you allocate and manage the memory, and this is something that we will be talking a lot more about as we move forward. Now, given the context of memory, the one sort of scary dragon that is present in any discussion of C is the pointer, right? And we will have a lot more to say about them as we move forward. The important thing is of course to understand that pointers ultimately just come down to a way of addressing something that is there in the storage of your system, right? The simpler that you create your mental model of what a pointer is, it probably becomes easier to appreciate that they are not that complex, provided that you literally think of them in terms of just literally their name. They are pointers, they point to a certain location in memory. How you use them is then up to you. We will be using quite a lot of these as we go through this course. And we will talk a lot more about how they are used in the context of embedded systems as well. So with all of this in mind, everything that I spoke about up to now was just general purpose C programming. So what is embedded C? Embedded C is largely C itself, and why it is useful is because, as we have already seen, the C language compiles into instructions that are very close to the hardware, which in turn means that by using it in the right context, we can directly manipulate hardware capabilities. It also, the fact that we are able to have fairly good control over the kind of instructions that get generated means that in a scenario where we have constrained resources, we have a limited amount of memory, a language like C could be very useful because it helps us to control how big our program becomes. So these are requirements for the highly optimized kind of operations that we need in embedded systems. Now, where do we use these? It could be consumer electronics, TV, kitchen, camera, things of that sort. It could be automotive, where things like real time and safety start playing a bigger role, or it could be medical, where safety as well as security and privacy of the data start to become very important. And most importantly, embedded systems tend to be systems that have very tight constraints. It could be that the entire thing needs to run off a battery, which means that there is a constraint on the amount of energy or power that's available to the system. It could be the size. You do not want a camera that's the size of a suitcase, you want something that can fit in your hand, right? You do not want a phone that needs a trolley to lug it around, you want something that can fit into your pocket, right? And of course, at the end of the day, you also care about the cost, right? So all of these are constraints on the development of a system. You cannot just have a big desktop or a tower kind of machine which sits under your desk and yes, has a very powerful graphics card and capabilities and lots of RAM and storage which allow you to do whatever you want, but becomes useless because you can't carry it around and use it when you need to. So those kinds of things are the constraints that embedded systems are working under, and embedded C helps us with sort of planning for those and meeting those constraints. There are a lot of similarities and differences between C and embedded C. On this side you can see that there's, this is a program that's written in the regular C language, and you can imagine that there's a printf statement out here which basically says enter some data. Presumably that comes out on some kind of a screen that you can see. And then there is a fgetS, a function which gets data from a standard input. Now if you think about it, what does that mean? For a person writing a C program, you call a function, you get a result, right? But how does that actually get implemented? That is where the embedded C starts playing a role. A similar kind of thing could be something where I actually define something called a sensor data register in embedded C, and as you will see, that turns out to be something which, a hexadecimal number in this case, which as we will see later is actually a pointer, a memory address. And the fact that I am declaring it as an int star, right, meaning it's a pointer to an integer, a pointer to an unsigned 8-bit integer in this case, allows me to then directly sort of write data into that value, and it will take whatever is there in the sensor data register and write it into that. And as we will see later, that actually does something which is the equivalent of a putC or a fputS, which literally takes some data, sends it out to a peripheral, and that peripheral has the hardware logic which knows how to display it or do something with it. It could be something as simple as turning on a button, right? Or in this case actually what we are doing is we are reading from the sensor data register, not writing to it. So it will be able to take a byte, right, from some memory location and store it into this variable that we call sensor data. It is very similar, in other words, to what this fgetS function is doing, except that this is directly doing it at the level of hardware, and it makes it very clear to you exactly what is being done. So in some sense these are just two examples of what code would look like. Both are C, both are valid C code. One of them is targeted more at an embedded system, the other is targeted at a general purpose C programming environment. So to summarize this portion, right, C is often used as the starting point for embedded programming. It's close to the hardware and it's easy to appreciate the importance of memory and resources when you use a language like C. Now, a lot of what we will be doing will be manipulating memory. It's in some sense a slight misuse of the concept of an address, which allows us to directly talk to the input and output hardware, right? We'll see how that works a little bit later on, but we'll not get into too much detail of how the hardware part of it works. Okay? So the kind of structures in C that are important for an embedded engineer to know, of course you need to know what data types are, what kind of control logic, conditionals, loops and so on are available, the idea of functions, modular programming, reusability, and of course memory and how to manage it. That is something we will be talking about a lot more as we proceed through the course.